Hi everyone. In previous lecture, we started a development of adaptive filter theory, and that we discussed the fundamentals of filtering, smoothing, and prediction, introduction to filtering. And now, in this lecture, we'll be going to cover linear optimum filtering, statement of the problem, principle of orthogonality, minimum mean square error, Wiener-Hauff equations, error performance, minimum mean square error. First, we'll start with the linear optimum filtering, the problem statement. In this chapter, we study a class of linear optimum discrete time filters known as collectively as Wiener filters. Wiener filter theory is formulated for the general case of complex valued stochastic process with the filter specified in terms of its impulse response. The reason for using complex valued time series is that in many practical situations, for example, like communications, radar, sonar, the observables are measured in baseband form. That's why we'll use this complex value time series in many practical situations because observations are in terms of baseband form. Baseband is used to designate a band of frequencies representing the original signal as delivered by the source of information. Now we'll begin this chapter by outlining the linear optimum filtering problem and setting the stage for examining the rest of the theory of the Wiener filter and its variants. First, we'll start with this linear optimum filtering problem statement. Then we will discuss in detail about the Wiener filter and its variants. Now consider this block diagram. This block diagram representation of the statistical filtering problem. This is the block diagram representation of the statistical filtering problem. Here, if you see this block diagram of this figure built around this linear discrete time filter, the filter input consists of time series u of 0, u of 1, u of 2, and the filter is itself characterized by the impulse response represented by the sequence W0, W1, W2, so on at some discrete time n. At some discrete time n, the filter produces an output denoted by the y of n. Right? Input simply the consists of time series u of 0, u of 1, u of 2, and the filter itself is characterized by the impulse response, which is represented by the sequence W0, W1, W2, and the output denoted by y of n. Here n, small n is at some discrete time n, this output is y of n. The output is used to provide an estimate of a desired response designated by d of n. Right. This output is used to provide an estimate of a desired response designated by d of n, with the filter input and the desired response representing single realizations of respective stochastic processes. The estimation is ordinarily accompanied by an error with statistical characteristics of its own. In particular, the estimation error E of n, right? Or simply estimation error, which is generally denoted by the E of n, is defined as the difference between the desired response D of n and the filter output y of n, right? The estimation error, which is generally denoted by the E of n, is simply the difference between the desired response, that means d of n, and the output y of n. Simply we can write it as e of n equals to d of n minus y of n. This is what here this, right? E of n is the estimated error, difference between the filter output and the desired response is error. E of n equal to d of n minus y of n. The requirement is to make the estimation error E of n, right? The requirement is to make the estimation error E of n as small as possible in some statistical sense. Here, the given things are for filter input U of n, desired response D of n, find the optimum filter coefficients, that is, those are the weights W of n. To make the estimation error as small as possible is a requirement. Now, two restrictions are placed in the filter. The restrictions are, first, the filter is linear. That is one of the thing, linear optimum filter. The first restriction is, first the filter is linear, which makes the mathematical analysis easy to handle. Then second one, the filter operates in discrete time, which makes it possible for the filter to be implemented using digital hardware or software. The filter operates in discrete time, which makes it possible for the filter to be implemented using digital circuitry, digital software, or digital hardware or software. But the final details of the filter specification depends on two choices. Those are, first one, whether the impulse response of the filter has infinite or in a finite or infinite duration. Final details of the filter specification depends on two choices, whether the impulse response of the filter has finite duration or infinite duration. Finite means FIR filter, this is IIR filter. Second choice is the type of statistical criteria used for the optimization. The type of statistical criteria used for the optimization. Here, the choice of FIR, finite duration impulse response, or an infinite duration impulse response, IIR, for the filter is dictated by the practical considerations, right? This choice of FIR or IIR is dictated by the practical considerations. The choice is a statistical criteria. The choice of statistical criteria for optimizing the filter design is influenced by mathematical traceability, mathematical tractability. Here, for the first, if we'll consider this case, whether the impulse response of the filter has FIR or AIR. Here, for the initial development of NR filter theory, we'll assume IR filter. So the theory includes FIR filter as a special case, right? Initially, we'll assume IR filters because FIR filters are the special case of IR filters. Then we'll confine our attention to the use of FIR filters because, but the main point here will confine most of the time to FIR filters because FIR filter is inherently stability. FIR filter is inherently stable since its structure involves the use of forward paths only. Here, most of the time we'll confine to this FIR filters rather than this IAR because of this FIR filter is inherently stable since its structure involves the use of forward paths only. On the other hand, if you come to this IAR filters, IAR filter involves both feed forward and feedback. So the presence of feedback in IIR means that portion of the filter output and possibly other internal variables in the filter are fed back to the input. So unless the filter is properly designed, feedback can in turn make it unstable, with the result that the filter oscillates. This kind of operation is clearly unacceptable. So FIR filters generally they provide stability. These IR filters are unstable. That's why most of the time we prefer FIR filters than IAR filters. That is one thing here we have to observe. Then when the filter is required to be adaptive, our course is adaptive signal processing. So when the filter is required to be adaptive, so inclusion of adaptivity combined with feedback that is inherently present in IR filter makes a difficult problem that is much more difficult to handle. This is why the reason the majority applications requiring the use of adaptivity uses FIR filters than IR filters. Even though IR filters demanding less even though IR filters requires less computational requirements, FIR filters are preferred one. Then coming to the next issue, that is the type of statistical criteria used for the optimization. Okay, now when we come to this second one, that statistical criteria used for the optimization, we find that there are indeed several criteria that suggest themselves. Specifically, here we may consider optimizing the filter design by minimizing the cost function, right? Here the main thing is optimization problem comes in this, the second choice. So how this optimization problem can be considered? Optimizing the filter design is simply minimizing cost function or index of performance. And here the possibilities for this optimization criteria are listed here. These are the three possibilities are there for the optimization criteria. Satisfy the statistical criteria used for the optimization. We can optimize by simply optimize filter design by simply minimizing the cost function. Here the cost function is, it may be MSE, LMS, etc., etc. Here the three possibilities are there. First one is the expectation of the absolute value of the estimation error. We will denote it by this symbol, expectation of modulus of E of n. Second possibility is mean square value of the estimation error, expectation of modulus of E of n whole square. Third possibility for this optimization criteria is expectation of higher powers, or expectation of third or higher powers of the absolute value of the estimation error, and this will generally denote it by this expression. Now option 2, this one, expectation square value, mean square value of the estimation error, this one. This has a clear advantage over other two, 1 and 3. 2, this possibility is having a clear advantage over this possibility and this 1 and 3, because it leads to, this second possibility leads to tractable mathematics. That is why this possibility is preferred over this and this possibility. In particular, the choice of the minimum mean square criteria results in a second order dependence for the cost function, dependent for the cost function on the unknown coefficients in the impulse response of the filter, right? Here the minimization of the mean square value of the mean square value of the error MSE is mathematically tractable. So for optimizing optimum filtering, or simply the optimize Now summarize the essence of the filtering problem with the following statement. We can simply summarize the essence of the filtering problem with this statement. Here, design a linear discrete time filter whose output y of n provides an estimate of desired response t of n given a set of input samples u of 0, u of 1, u of 2, so on, such that the mean square value of the estimation error e of n, defined as the difference between the desired response d of n and the actual response, is minimized. Here, by this statement, we are summarizing the essence of filtering problem. We develop mathematical solution to this statistical optimization problem. Here what we'll do is, in the next sections we'll develop mathematical solutions to this statistical optimization problem following two entirely different approaches which are complementary. What we'll do is we will develop two mathematical solutions or two different approaches which are complementary to each other. One approach leads to the development of an important theorem commonly known as principle of orthogonality. The first approach is the principle of orthogonality, and the second approach highlights the error performance surface that describes the second order dependence of the cost function on the filter coefficients. And we'll proceed by simply deriving the principle of orthogonality first, because the derivation is relatively simple and the principle is highly insightful. The first approach is principle of orthogonality. The second approach is, it's a simple, the error performance surface minimum mean square error. That is the second approach. Let's start this principle of orthogonality first. Thank you.